Hi everyone, I'm Jose Wesley. I'm pursuing a master's degree at the Federal University of Minas Gerais in Brazil under the supervision of Professor Fernando Pereira. Today I'm going to talk to you about the work Automatic Inspection of Program State for Debugging and Verification Purposes. This project is being conducted since the beginning of 2020 and we are working in collaboration with Dr. Chunhua Liao, a colleague from the Lawrence Livermore National Laboratory from the United States. The goal of this project is to develop a new technique that is capable of reporting the state of a program. But what is a program state? The program state is formed by the values that the program manipulates. Such values are stored in different memory regions, like stack or heap, or in static allocated memory like global variables. The ability to inspect the values that form this state is useful for many purposes, like debugging and automatic benchmark generation, data visualization, and program verification. However, it is difficult to correctly identify these memory regions in type-unsafe languages. In the garbage collection community, those languages are known as incomparative. Examples of such languages include C, C++, and most of the assembly dialects. Given this scenario and the fact that, although important, efficiency is not the main concern in this context, we propose a new approach to report the internal state of a program. We propose a static program transformation that inserts in a program verification routines called inspection points. A inspection point is a static notion, a point after a statement of a program where the state can be proved. For example, in this program, we can identify 4 inspection points, marked as A, B, C, and D. In this work, we create inspection points at the exit point of functions. From inspection points, we create inspection traces, which are collections of points traversing during the execution of a program. And for each inspection trace, we can inspect the state of a program at that point. Our solution is able to track values in different memory regions. For instance, the static allocated variables, or the variables on the stack of the functions, and the values allocated in the heap. We can traverse the heap like a tracing-based garbage collector does, and due to this ability of traversing the heap, we can reconstruct sparse data structures like lists and trees. Our solution is implemented in LLVM and is fully automatic, and it's a customizable tool. A user can choose which functions and memory regions will be inspected. We have conducted an experiment to investigate what is the impact of our technique in the running time of the programs. We tested in 4 benchmarks that make use of stack and heap allocated data: BST, a binary search tree; fact, the non-recursive factorial function; linked, an implementation of a linked list; and KeyAS, a program that solves a series of quadratic equations and stores the solutions continuously in the heap. We measure the running time of each program, original and instrumented. This figure reports the overhead of 2 modes of inspections without printing the data. In the first, we track states of variables allocated statically or on the stack. In the second, we also consider heap allocations. Within each mode, we can instrument the return point of every function or only of main function. Each benchmark was executed 10 times and the chart shows the average running time. The value in black boxes corresponding to instrumentation overhead. When only the local variables are inspected, the overhead reduces in the majority of the benchmarks, due to the fact that the heap is not traversed at the end of each function call. And this figure shows that inspect only the main function reduces even further the overhead. This mode of instrumentation is useful, for instance, to add verifiable outputs to benchmarks automatically produced. To give you some perspective on this overhead, notice that just the time to print the results would already doubled it. The fact is that the program manipulates a lot of data, and if we want to keep track of all this data, a large overhead cannot be avoided. Although the overhead is huge in some cases, this is a work in progress, and there are many opportunities for improvement, which we are already engaging on it. So that's all I had to present today. If you get interested in this work, please get in touch, and you can also watch the long version of this presentation. Thanks everyone for watching.